Let me begin by thanking particularly Alok Mitra for asking me to give a talk in this very important meeting celebrating the life and work of one of the most distinguished physicists, Professor A.N. Mitra. Which I was not his student, but yes, in the later years, we did meet, and it was very interesting that he will always ask some conceptual issues. And so I'm with a very fond memories. I dedicate this talk to Professor Mitra. Let's begin with. The idea here was that how do we distinguish a fundamental force from the other thing? And the question I said is that its dynamics should not be prescribed, but should follow from some general principle. So that's the plan of the talk, to say that the fundamental force dynamics should follow from some general principle of conservation of something or the geometry. So, for example, the Newton's and Coulomb's laws are driven by the conservation of flux. That's how you get the inverse square law. Now let's come to begin with that in the absence of force, what should be the state of space and time? So we want to first start with the characterize the space-time when in the absence of all forces. And in doing this, the two constants of space-time structure will emerge. And they emerge without any reference to any dynamics or any force. And the fundamental forces then will emerge when the space-time becomes inhomogeneous. So homogeneous space-time is free of all forces. When it becomes inhomogeneous, then the fundamental forces emerge. And of course, which space-time will depend on what sort of, what kind of force we are referring to. So let us begin from the beginning. When we say space is homogeneous, we can freely exchange x and y. And the free space-time is homogeneous and isotropic. But also the free space-time does not distinguish between space and time. So time is also homogeneous. So whatever I do to x and y, I should be able to do the same thing for x and t. But then you pounce upon me to say that no, their dimensions don't match. So you have to bring the things on the same dimension. So then my question is, yes, this is the general principle, homogeneity, which has to be respected. So if the dimensions don't match, make them match. And for that, to make the dimension match, we need a universal velocity. To bring t and x on the same footing, and this is how emerges the first constant of space-time structure, the universal velocity c. So what does the c does? It binds space and time together into space-time. So now we go from the three space in the three space to one time, to we go to a four-dimensional space-time. So we have a one paradigm shift that we live in a four-dimensional space-time, not really in a three space and time. So free space-time, so in absence of this, the free space-time should be homogeneous, which would mean the space is homogeneous and isotropic and time is homogeneous. The next question is, what should be its geometry? A natural answer is, a geometry must be also homogeneous. Now, geometry is defined by the Riemann curvature. So Riemann curvature must be homogeneous, means Riemann curvature must be covariantly constant. And hence, I should be able to write Riemann curvature in something which is constant relative to the covariant derivative. And that is, of course, the metric. So you write the Riemann curvature, some constant lambda to give the dimension of 1 over length square, and the combination of the metric, the metric coefficients respecting the symmetry of the Riemann curvature. So we have naturally come to the homogeneous space-time, which is free of all forces, is a space-time of constant curvature, not necessarily of zero curvature. And that constant curvature is what is that we denote by lambda, which could be positive, negative, or zero. And what it should be, that it should be left for the experiments and observation to determine. So at the moment, so the free space-time has this homogeneous geometry of constant curvature. So lambda thus emerges the second constant of space-time structure on the same footing as the universal velocity c. And these are two the most fundamental constants we have, because no other constant yet has been synthesized in the space-time structure. Having said that, now let's go further. What happens when space-time becomes inhomogeneous? Again, a very simple thing, right from the classical mechanics, we know that inhomogeneity signals the presence of a force. So now the question is, what should determine its dynamics? And the answer to that is that I have only the space-time and its curvature. There's nothing else at our disposal, so it has to, the dynamics of this force arising out of the inhomogeneity of space-time should also arise from the space-time curvature itself. So now we ask the question, is there anything we know for as a property of the Riemann curvature? In differential geometry, there is a very celebrated identity called the Bianchi identity, saying that d square equal to 0. The properly defined derivative twice d square is identically 0, which the John Wheeler famously had termed in a poetic way that boundary of boundary is 0. And that is what is the geometric way of expression of conservation law. Now, well-known examples of this d square equal to 0, we all know, but we never recognize them as a differential geometric statements. Curl of a gradient is 0. The divergence of a curl is 0. So you have a scalar field, you have taken care of the vector field, Now you say that if you go to the higher order, you have a tensor field. Then the analog of the next order thing, the cousin of this is that Bianchi anti-symmetrized derivative of the Riemann tensor must zero. This is what is called the Bianchi identity. So we have a Riemann curvature, its anti-symmetrized derivatives is identically zero. So this is given by differential geometry. We have nothing which is, we don't have anything from outside. Now, any tensor equation you have or any tensor relation you have, simplest thing you can do is to contract it, take its trace. And ask first the question is, find a trace of contraction which is non-vacuous. And this is the only what you have written here is the non-vacuous trace of the Bianchi identity. So you're contracting this, and what does it give us? This gives us a second-rank symmetric tensor GAB with vanishing divergence. And this GAB is given in terms of the Ricci and the Ricci scalar. I think the scalar has gone out this thing. And the Ricci is the first contraction of Riemann. So as a matter of fact, what we obtained, everything started from the Riemann. So we obtained a second-rank symmetric tensor, which is essentially a creature of Riemann tensor. So we have this, we come up to this, right? Now we say that if a force is universal, by which we mean that the force which links to everything that physically exists, and which means hence it has to be present everywhere. It should therefore be described by some universal entity which is present everywhere and which is shared equally by all that exist there. So that can't be anything other than the space-time itself. And the force should be described by then the inhomogeneity of this space-time, and that is when the Riemann curvature is inhomogeneous. So the force could, another way of looking at it, should arise from the geometry of the space-time through the Riemann curvature. The dynamics that follows would be the dynamics of that universal force. So now let's get back to this. So what we were? We obtained a divergence-free second-rank tensor, which is GAB. Now in a simple farmer's way of integrating, let us integrate this equation. So what the simplest way to do is to say, okay, write this GAB, add a constant of integration relative to covariant derivative, that is your lambda GAB, and write another proportional to a tensor TAB, demanding that it is symmetric and its divergence is zero. So this is a formal way of doing this. Now we know on the left-hand side is a creature of Riemann tensor. And the Riemann tensor is involves the second derivative of the metric and square of the first derivative. So on the left-hand side, I have a second order differential operator analog of del square phi. then you would say that on the right-hand side, if I could identify a source, then it becomes an equation of motion for this force. So the thing here, the new thing which I have, lambda is GAB is a constant of integration, so that's nothing. Is a TAB. Now the TAB is the source which makes space-time inhomogeneous for all particles, which means the TAB should be a measure of some property which is universally shared by all that physically exists. And that property then is uniquely the energy momentum. So if I identify TAB with energy momentum, then the equation 5 above is the equation of motion of Einstein gravity. So in a very simple way, we derive the equation of motion for Einstein gravity from when space-time becomes inhomogeneous. So here the question which I wanted to say, sorry, so that the universal force of gravity, its dynamics is determined by the geometry of the Riemannian space-time and its curvature, without adding anything to no prescription of any kind from anywhere. So that's my main message from this talk. So what we say. Now you see that maximally symmetric homogeneous space-time, which is free of all forces, is of constant curvature, not necessarily of zero curvature. When that curvature is inhomogeneous, when force is present, then curvature becomes inhomogeneous. In contrast, our textbook view is no gravity means Riemann curvature is zero. Now, which is in our language saying the lambda is zero, which you have put it by hand. You demand this. But actually, it should be left to the experiment to say whether lambda is zero or non-zero. In this picture, paradoxically, you have maximally symmetric space-time, homogeneous space-time of constant curvature, which has non-zero curvature, and the space-time is homogeneous, but curvature is non-zero. Hence, but it has still, so that constant curvature will give you a non-trivial dynamics. As a matter of fact, maximal symmetric homogeneous space-time should have no dynamics. It should be a free of thing. In a new perspective, in our way of looking at it is, no force, absence of gravity means space-time is homogeneous. Presence of force, space-time is inhomogeneous. As it is in the classical mechanics, you go from homogeneous to non-inhomogeneous, you come from the zero force to the force. So there is smooth transition from homogeneous to inhomogeneous as force appears. C and lambda are two constants of free homogeneous space-time. They are the most fundamental constants that I have. Now there is another one ticklish question we have to address is of the vacuum energy. Now vacuum energy is created by the fluctuations produced in the vacuum produced by the matter fields. And since gravity is universal, all forms of energy must gravitate. So that is true that the vacuum energy which is taken care of should gravitate. And when you try to compute write a stress tensor for the vacuum energy by all your renormalizations, throwing away the infinities, it has the same form as the lambda GM. And that is where lambda gets slated against the Planck length. And then you have this monumental discrepancy of 120 orders of magnitude. So lambda gets beaten by Planck length. But here you should know that that lambda comes out as a natural fundamental property of a homogeneous spacetime. But that's right. Now the question here is, so we have this conflict here. Vacuum energy must gravitate. Then the question we should ask is, should it gravitate through a stress tensor? And generally you say that yes, all matter fields gravitate through a stress tensor. Should it gravitate this? And that's the question which we want to ask. That we can forget about. But we say that gravity is universal, energy, any form must gravitate, so vacuum energy must also gravitate. The question we are asking, should it gravitate through a stress tensor? So the thing which would require is that gravitational energy does not have, vacuum energy does not have an independent existence of its own. It is created by the matter fields that produce the vacuum fluctuations. So it is a secondary source of gravity. And the answer is the secondary source, that should it sit on the right-hand side of the equation along with the mother, the matter field. This other thing we said, that one other question is, have we not done something similar which you have taken care? Gravitational field energy or gravitational self-interaction. That is also a secondary source created by matter. And we wrote no stress tensor for that. It was the gravitational field energy or self-interaction does not interact with stress tensor, but it interacts by enlarging the framework. So as a matter of fact, this asks for that it cannot be incorporated in the Newtonian theory. We need a new theory, and it is incorporated in the curvature of three space. Now, this we really do not recognize because the space-time itself is curved, and nobody bothers about this. But if you really want to see that in the Schwarzschild solution, how is the self-interaction included, then you will find that it is included in the space curvature. So for example, if you keep the dr square coefficient 1 and write only 1 plus 2 phi for dt square, it will incorporate the Newtonian gravity, R double dot equal to grade phi. But when you include the dr square coefficient inverse of the JTT, then what happens is the self-interaction gets, the term self-interaction term gets worked out, and it has, and the curvature, the effect of the self-interaction goes into curving the space. So this is essentially to saying, coming from the flat three space to curved three space incorporates automatically the self-interaction or the gravitational field energy. Then, so in general, you have the inverse square law remains valid in GR, and your is the space curvature which takes. So now the question is, what the vacuum energy is on the same footing as the gravitational energy. If the gravitational energy does not interact through stress tensor, so must vacuum energy must out. And so we require a enlargement of the framework. Another argument you can say that, you see, this is your force you have for the particle. M into acceleration is the force. Its fluid thing is rho plus P dU dt equal to the gradient of pressure. Rho plus P here is the inertial density, which is an analog of mass. For the particle, when mass vanished, we needed a new theory to incorporate its motions. So we needed a special relativity. Similarly, here, rho plus P is 0 for the lambda. If you take the lambda as the matter field, so you will need a new theory for this. It cannot be incorporated in the existing general relativity. So you need a new theory, and that new theory we will not know unless we have a quantum theory of gravity. So vacuum energy must gravitate like the all. So the general principle we say that all the secondary sources must gravitate through enlarging the framework, not through the stress tensor. And I would say, to me, one of the compelling motivation for vacuum for the quantum gravity is to include the gravitational interaction of vacuum energy. Once that is realized, lambda is free of the Planck length. You can otherwise say in this 120 orders magnitude, you can make a more meaningful statement that in Planck area, the universe measures this much. Okay. So lambda was determined in 1997 in the supernova explosion after 100 years of its introduction. Had Einstein followed this argument, he would have realized, oh, I'm doing badly. Then he probably would have made the greatest prediction of his time that there would be sometime in future, lambda will dominate over the expansion of the universe, and you will have an accelerated expansion of the universe. No need for a dark energy or the phantom things or anything that kind. Lambda, that's, I think that's okay. Now we say, okay, this all was fine. Now we say, how do we talk about the other fields? So the question we ask is, the next thing is that a force which links to a particular charge. So you have a gauge vector field. Now here you ask, what is the relevant geometry, relevant space-time geometry? And that turns out that the principal tangent bundle of space-time.
Professor Dadhich, you have 5 minutes.
I'll like in 2 minutes. I'll keep it within this.
Okay.
So that its curvature is given by the two forms which satisfy the Bianchi identity, which means that it is derived as a curve. So it's antisymmetric. Since it is antisymmetric, its double divergence is identical 0. And which, like as we integrated the Bianchi identity, you similarly integrate this, gives you the divergence of F as the for current, conserved current. And that's what gives you the Maxwell field. And so you get the, now the Maxwell field, so you have a vector field. So when there you can now attach some other symmetries. So when you have a U1 symmetry, then it is your abelian gauge field you get. But now you say, okay, that is from SO1, abelian. Now you can get a non-abelian you can have SO2 and SO3, your Youngman's field, everything goes same way, except that now your derivative, you have to define the gauge invariant covariant derivative. The rest of the thing what we did for the Maxwell field goes through the same argument. And again, you will have the dynamics of these fields coming from the Bianchi identity of the tangent bundle space. So that's that. So the question is, the dynamics is given by the geometry of the relevant spacetime. And lastly, a minute to go, I can say we have four fundamental forces, and they're defined by the linkage, what it links to and what the range is. When you say the force is universal, that is universal linkage and long range, it's uniquely Einstein gravity. All other forces will come from them as you relax this property. If you relax A and keep B, you get the Maxwell field. Then you say that you relax B, the short range, and linkage to all massive particles. Massive because of that short range to be respected. That will correspond to your weak force. And finally, relax both. You will have a picture of that will be your strong force. A last thing we can, does we have a unified picture? Does this picture suggest something? Let's say this. Anything that participates in weak force must have a mass. So that's prediction that the neutrino must have a non-zero mass. Then there are duality relations. The weak and the electric are complementary to each other. Similarly, the gravity and the strong are complementary to each other. So in some relevant space-time, I think someday these dualities should be fully established. Let's stop here. Thank you.
Okay, thank you very much, Professor Dadhich. The talk is open for questions. I don't see any hands raised for questions. I think we thank Professor Dadhich again, and I'd like to thank all the speakers of this session for their interesting talks and sticking to the time. And with this, I'll hand the floor back to Professor Alok Mishra.